Hi everyone, my name is Shoichi Hasegawa and I am a doctoral student at Ritsumeikan University in Japan. In this presentation, I will introduce to my research on inferring place-object relationship by integrating probabilistic logic and multimodal spatial concepts. First, the introduction. Let me start with the background of my research. One of the desired tasks of daily life service robot is to assist people with their household chores. For example, delivering the specified object to a user or tidying up scattered objects. To achieve this task, it's important to understand which object is likely to be in each place. In other words, evaluate the object existence probability in each place. However, the object existence probability in each place varied depending on each environment, and thus the robot needs to learn it from data obtained in each environment. Therefore, the goal of my research is twofold. One, reducing the cost of on-site learning in a new environment by common sense knowledge. And two, predicating the place where an undefined object is located by probabilistic logical inference. Here, undefined objects are defined as objects for which the probability of existence for each place has not been calculated yet. To illustrate, let's assume the situation in which the robot brings a target object to a user, in this case, a sheep doll. First, the user commands the robot with a sentence like, look for the sheep doll. Since no information about where the robot should search it is given, the robot infers a place where the object exists based on common sense knowledge. So, for example, as a sheep doll belongs to the doll category, it is likely to be located in same place as other doll. Then, based on multimodal data obtained in environment, the robot also infers place-object relationship using spatial concept model. In other words, what place is what object in the environment. Finally, after integration both inferred knowledge, the robot can find the target object in a small number of searches. With our approach, the robot can reduce the cost of on-site learning and find undefined objects. The research question is, how much can the robot reduce the on-site learning cost by incorporating logical inference based on common sense knowledge into on-site learning? The task performed by the robot is to move between rooms and searches for objects after user gives the robot instruction to search for objects. For evaluation, we consider how much we can reduce the number of learning iterations or places to find an object in a single room visit. The research purpose is to verify whether the combination of on-site learning and probabilistic logical inference can reduce the cost of on-site learning cost for finding a specific object in a new environment. Next, I will introduce two related works. Regarding leveraging common sense knowledge for understanding spatial semantics, Jiang combined a large amount of image data and ontologies to provide common sense knowledge to a robot for more efficient object searching. For example, they calculated the object existence probability in each place by counting the labeled object in the image, and they defined the place-object relationship with symbolic statements like cup is on cabinet. However, it was difficult to handle objects for which the object existence probability was not given in advance. In our approach, we use probabilistic logical inference to solve this problem. Regarding searching for undefined objects with robots, Vega uses probabilistic logic, which extends predicate logic to handle probabilistic events. Probabilistic logic can be described by assigning probability value to predicate logic, as shown below. However, compared to Vega approach, where the semantic map was entirely defined by the human and given to the robot, we construct the semantic map based on the robot's own observation. Regarding on-site multimodal learning, Taniguchi proposed SPOOK-SLAM, a probabilistic generative model based on Bayesian theory that simultaneously generates spatial concept, vocabulary, and map. And the right figure shows a graphical model which consists of several modules and allows cross-modal inference. Using Spokoslam, the robot can construct statistical knowledge as which object is likely to be in each place through observation. However, the robot needs to obtain a certain amount of observation in the environment. So in the research, we reduce the on-site learning cost by using common sense knowledge. Next, I will give an overview of our proposed method and explain each module. First, probabilistic prologue or problog is used as probabilistic logical language for probabilistic logic. Describing knowledge in problog is as follows: the object category, object existence probability, and the predicate expression of object and places. When the query "where does a sheep doll exist" is given, the solution is derived by repeating by resolution and unification. And this allows the robot to infer knowledge about objects with undefined place in the form environment. Second, a model-based Spokoslam, which allows the robot to learn spatial concepts through multimodal information, is used to learn on the on-site environment. In this graphical model, the parameters of the probability distribution are learned from sequential Bayesian estimation with the particle filters. In addition, our model can perform cross-model inference from object level to place region. This allows the robot to learn the relationship between objects and places. The third, I will explain the integration of probability distribution. Using problog, we obtain the construct by summing a possible solution to a query based on distribution semantics. And regarding on-site learning, we derive the inference formula from Bayesian theorem by using parameters of probability distribution obtained by on-site learning. The probability distribution is then integrated by weighted averaging. Finally, the robot searches for places related to target object. First, to give the object name, we calculate the probability of the region where the target object exists, and the search is performed in the order of object existence probability. The averaging of Gaussian distribution is set as destination. The following movie shows the probabilistic planning. In this section, I will describe the experiment. Its purpose is to verify how much the on-site learning cost can be reduced by leveraging logical inference based on common sense knowledge when searching for objects containing undefined objects. Learning cost in this study refers to the number of room visits necessary for learning places. The procedure is follows. First, we construct common sense knowledge to be used by the robot. Next, the robots learn places in the on-site environment. Then, object search is performed using the parameter obtained from learning. After the experiment, we evaluate the result against the comparison methods. The following comparison methods were prepared: a method using on-site learning, common sense knowledge, and combining on-site learning and common sense knowledge, and our approach. First, we constructed common sense knowledge. We conducted a questionnaire survey on what objects are likely to be placed in which places. From the result of questionnaire, the object existence probability was calculated by smoothing. The object category existence probability was also calculated. These were used common sense knowledge for probabilistic logic. Next, I will explain the on-site learning in the environment. Experiments were conducted in a simulated environment with 8 undefined objects. During the on-site learning, the robot learned which place is called by fact name for each area on the occupied grid map. After the Spokeslam was used to learn the object existence probability at each place, the right movie shows the learning phase in which the robot learned place-object relationship based on observation. The order of learning was living room, bedroom, kitchen, and bathroom. The robot performed a search task using the parameter of spatial concept obtained at each learning. Next, I will explain the object search task. In this task, the user gives the robot object name. and the robot moves between rooms to search for objects. In this case, the robot searches 24 objects. The good result is shown the left movie and bad result is right. In the left movie, the object is located in one room, while in right movie, it takes 3 rooms to reach the place. Here the experiment result. For the evaluation criteria, we use the proportion of objects found by the robot in one search room visit and set 80% as a satisfaction threshold. The proposed method achieves more than 80%, where the number of room visits in the training 5 times, while the other method takes more than 8 times. This shows the proposed method can reduce the learning cost by a factor of 1.6 or more compared to the other methods. We also attempt the task of tidying up undefined objects in real world using our approach. The video below shows the task of tidying up a duck sponge. It shows the robot is able to infer the likely place of the object by using probabilistic logical inference. After inferring the place where the object exists, the robot moves to the destination. To summarize, we proposed model combine probabilistic logical inference and on-site learning. Experimental results show that our approach can reduce the learning cost by a factor of 1.6 over. In future works, we utilize large language models as a method of acquiring the object existence probability in each place. That's all. Thank you for listening to my research presentation.